0.7492. So I've got that difference that will always be there, depending on how the part comes off. It will be, that's the smallest, which is our allowance. Okay. Now the bottom section is down there just to look at this, where you're looking at maximum material condition and least material condition. So, smallest hole, these first ones right here, this is allowance. So those first three are allowance, or the difference between the two at maximum material condition. The last three are analyzing it at least material condition. So you just grab those numbers. So our smallest hole is 0.7500. My largest shaft is 0.7492. My difference is a positive well, it tells us right in there, positive 0.0008. So I have 8 10,000ths. Then we'll look at it at least material condition. So I look for my largest hole, which is 0.7512. I look for my smallest shaft, which is 0.7484. 4 to 12 is an 8. Goes to 10, that's a 2. I got 0.0028. Again, somebody might want to check my math.
You add them for a certain?
No, I subtract it. Okay, you got a minus sign, minus a minus. If I'm doing a clearance fit, both of these better be positive. If I'm doing an interference fit, what do you think both those answers are going to be? Negative. If I'm doing a transition fit, I will get a positive and a negative.
What?
Least material condition would be positive. Maximum material condition would be negative. For a transitional fit, because for transitional, remember, it can be both. In fact, it has to be both. Now I have all the information I need. So I can come in and do my shaft a couple different ways. So when I'm doing this shaft, I can do it as a limit dimension. Okay. So if I was tolerancing my shaft, it's this one right here. Okay, so I can put this up as diameter and use my limits, because this has got to be 0.7492 to 0.7484. That's a direct tolerance, correct? I can also use lateral dimension, 0.7500 plus, I think for this one, what was it, 0? No, it wasn't. Yeah, minus. I can't see the thing. Is it 0.00?
Which one are you?
I'm looking for the upper.
For the shaft?
Yeah, for the shaft. I'm looking at the shaft. It's 0.008, right? So
Yeah.
this would be a minus 0.0008, and it would also be a minus 0.0016.
Both of those dimensions work? Or
Both of those work. Some firms, I've seen this on some drawings where they don't put any of this. They would put, right here, they would put diameter 0.7500, comma, RC4. Yep, and the machinist would then go look it up.
Seems a lot easier.
Let's not use this in here. We're going to use one of these two methods. Now, what do I draw them at? Draw them both at the basic size. The dimension will give them all the information they need. Okay, so I would draw my shaft at a diameter of 0.75, even though it's not going to be built there. I'm going to draw my hole at 0.75. In one condition, the hole does come off at 0.75, right? That's the lower limit for the hole. But all other conditions it's going to be larger than that. But I got to pick something, so I'm just going to draw them both at 0.75 as a size. Can you see how they work? See? Now this thing will work guaranteed in this condition if that's what we needed for the part to perform its job. Kind of nice stuff. In essence, other people have taken time, sat down in laboratories, can machine this stuff up, figured it all out, put it under operating conditions, prototyping, and figured out, hey, this is working the way I need it to in this condition. Let's go ahead and document this so the next person down the road doesn't have to pay for all this prototyping and lab work to get this thing to work right. That's in essence why we're doing these and why these are documented. Any questions or comments or thoughts?
Is it the same process on the other ones, like LT,
Yeah, they have different charts.
It is.
Same thing.
So what I'd like you to do is finish this sheet out. I'm not going to grade the first column. I hope you got it right. But I will look at the next two to make sure your numbers are right. I'd like you to look at, again, your basic size doesn't change, 0.75, 0.75. Yes.
Question, in architectural, how does this work? Is those, nothing's ever square or straight or whatever. How does you put limits on that, or do you, or is that taken care of by the drywall? How is the limits done there? Or see you next semester?
Well, I said this, well, at the start, I said this is a picture of things that we use in every industry, where we have documented items. In architectural, this does not apply.
Yeah.
Okay? It doesn't apply. This is a mechanical function. But,
You have to have limits.
oh yeah, we do have limits. Architectural is a standard tolerance of a 16.
Okay.
Okay? And if no tolerances are listed in architectural, that's what you use. And that was defined by the AIA, or American Institute of Architects. And we'll talk about that when we get to that. But what you might have is standards for the architectural world. Gabe, would you go grab one of those two blue binders right over there? Just grab one of them and hold it up.
IRC.
It's on the far right top shelf. Okay. So if you're doing residential construction, there is your machinery's handbook. That's the International Residential Code.
And it sucks.
If you're doing commercial, yeah, I might have taken them off because they were so old. If you're doing commercial work, you're actually using the International Building Code, or the IBC. Okay? And that has all ADA, American Disabilities Act, in it. It's got electrical, everything in it. And those are your machinery's handbooks. It's kind of funny, everybody, I think Angie came in and mentioned, oh, I want to do architecture, now I'm loving this. I bet you half or better of all of you said I want to do architecture. Well, when we get to architecture and we start throwing that book out and saying, hey, you got to follow this code, you got to follow this code, you got to follow this code, you're going to sit there, well, maybe I don't want to do this. I do get a big switch on that, but we'll see. I like codes. They tell me how to do things I have never built. They're a good thing. They protect the consumer too. But anyway, that's all I really had for today. Now, no, it isn't all I had. I did have one other thing. I wanted to give out your last assignment. Some of you already have part of this, but you don't have all of it.
Ooh, that looks like.
8. If you're wondering where 6 and 7 are, we're not doing them. So I didn't print them off for you. So you've got drawing 8. That one's fairly straightforward, I think. I did want to do this because we're going to use a scale of 1 to 2, but this has metric threads in it. Okay, so you got to look those up and deal with that a little bit. I think this one's pretty straightforward. If you got questions on it, come and see me. The next one, IDM 9. Here we're going to, you can consider this, if you are familiar with some of the terminologies of education, I'd consider this a capstone project in that we're going to take the entire program and boil it down. Okay, so we're going to do some direct tolerancing. We're going to use multiple significant figures and get 2 mating parts that work together. Okay. So again, you're going to be using some fits in here. We're going to provide a chart like you're looking at right now to show how this thing's going to operate together. You're given a bunch of information for your tolerancing down below. In essence, we're not going to draw this whole thing. This is in your text, by the way, in a later chapter. So in essence, this is a little hand vise. Okay, so we've got these 2 blocks. Okay, they're going to sit on these 2 pins so we can slide them together. The spring is going to push them apart so that they stay apart. This piece right here keeps it from popping off. And it's also the tightening device. As I screw that down, it takes that top block and pushes it down. My clamping surface is here and here. So I can then hold things in there and clamp them. Okay, so in essence, this is a vise. What you're going to look at is how these pins work with this hole. Okay. Now again, this is a vise, okay, and it's got to open and close constantly. So we do not want an interference fit on these, right? Because it's got to get back apart so I can remove something, put something else in. I don't want such a loose fit that as I clamp in this thing down, it starts spreading, right? Because I've got a bunch of room in this hole and it's going to spread apart and go sideways. Okay, so I need a tight enough fit that I don't get a lot of wiggle, but I can get it apart easily. But I think that in the instructions I said use an RC4 fit. Is that correct? On those 2? And be on the first page of the instructions. Okay. So we're going to use that
Yeah.
RC4 fit.
It does.
Keep in mind you've got a different size. I do change some of the dimensional information on this. You are given the isometric views of the 2 parts you're going to do on the next page. So I changed this size of this hole to match up with the pin. And I changed the pin also. I think I'm going 7/16, right? I went to a nominal size versus this kind of weird size, 0.4. This one calls as an LN. Okay, that's an interference fit. Okay. We changed that. That's not an LN fit now. It's an RC4 fit. Which, kind of weird how they kind of screwed up here on the picture. Because anytime you have mating parts, they should be the same fit, right? Because they work together. All right, so in essence, you're going to do this. You are asked to do some other things. I do need some surfaces finished. Okay. When we do a finished surface, how do we do it? I would like you to use the general surface finishing symbol for this. It's back in chapter 10. And in essence, you apply it everywhere you see the edge view. So as an example, let's say I'm getting this guy and I'm drawing it. Okay, my right side view is going to look something like this. Okay. And then I got some holes that come through. This guy's counterbore where the spring comes in, whatever it does. Then I've got these 2 out here. And again, you can do sections, you can do all this stuff on this drawing. Now, what I asked you to do, I think, is do a finish. So if you look in chapter 10, that little upside down V is a finish mark. That's called a general finish mark. you apply it wherever you see the edge view of the surface in indication. So it might occur several times. That would then reference into the notes. So on my general notes, I'm going to have a note down there that says FAO to, and do I got 63 micro inches?
No.
Isn't that what I finished that surface at?
Oh, yeah.
I think I said finish all mating surfaces.
This
Yep.
is.
When I get to the top view of this thing, I've got a circle, circle, circle. Are these two finished? Are they mating surfaces? Yes, they are. Okay. So again, I would have that little V sitting in there because I see the edge view there. I don't put on hidden lines.
Do you need to put one on the outside?
All the surfaces. No, I don't think this one mates. Because you've got this little one. This is the mating, right? It's mating with some part you're clamping.
Oh, okay.
This would be a finished surface because that's mating with the lower block.
So if it touches something else, basically.
Yeah, it's got to interact with another surface. And again, why would we do that? So I can clamp it down and I don't have some pitting or something that's going to kick that stuff off to the side. Micro inch is a pretty common term. You basically are dividing by, what, 100, I believe, for a micro? So when I say 0.63, that's 0.0063 is what the machinist would use. Okay, you're going to have to do a little thought on this one. You're going to be using tolerancing. I do ask for separate significant figures based on a size dimension or a location dimension. In essence, we're getting into the not only the manufacture of the part, but the performance of the part when we start looking at all this. Okay, we're trying to extend the life. We're trying to get it to do the job in question. Fun little project. You're going to have to think about it a little bit. I always like a mental challenge. Hope you do too. If you got any questions on it, give me a holler. I will kind of preview this a little bit tomorrow after the test review.
Is this due for the test?
No. Let's make 4B due today, 5 tomorrow. We'll be a couple days before you get an assignment on the next one, so not 8 will be probably Friday. This one will probably be due around Tuesday of next week. You're drawing both pieces on the same sheet too, by the way. All right, so that's all I've got for today. Any questions for me? Okay, thank you for your time.